Oh, thanks, Steve. Hello, everybody. My name is Trevor Chandler, and about a year ago I did a talk on astronomy misconceptions, part 1. Some of you may have been here for that one. If not, this is on the same kind of topic. I was curious about this because I wanted to, first of all, know if I had any misconceptions, and if I'm going to be trying to teach astronomy, I wanted to be aware what the misconceptions were. So I found an article, and I found out that there were some research done about astronomical preconceptions, and this, the author of this article, Trevor Chandler, discovered that there are quite a number of them that students and teachers have, and they have these preconceptions about different astronomical concepts. These misconceptions, they exist even prior to teaching. People just sort of develop them in life. The ideas they have are kind of, not in line with the accepted scientific thought. So they're commonly held. A lot of different people have them. It's not like just one person has a strange idea. It's like it's the same misconceptions held by a lot of different people. So it's embedded he reported it's embedded in larger knowledge structures. What he meant by that is just it's so embedded that even teachers have these misconceptions. So teachers are teaching the wrong astronomical thing idea. And because of that, it's really hard to change that misconception and get people sort of thinking the way things really are. So what he did, he developed this huge multiple choice question which he administered to teachers and students, and this quiz had each question consisted of 5 possibilities. One of them was the correct scientific answer, and the other ones were the most popular misconceptions. And he wanted to see what people were thinking, what misconceptions were common. So these are some of the questions from that. Maybe you'll find them interesting. Okay, so here we are, Friday after work. You've had a long work week, and we're doing math and a quiz. It's like, what have I signed up for? But there's no getting. If you're interested in astronomy, there's really no getting away from mathematics, just even a little bit of mathematics to kind of understand, because you're dealing with numbers, and some of the numbers are enormous that we're dealing with. So a lot of astronomers use scientific notation. So scientific notation is just a way of taking a really big number and making it smaller so it's more easier to understand. So here is one quiz he had. He had this number here, 25,600,000, converting it to scientific notation. And here's some of the possibilities here. Anybody?
C.
Anybody? C. So we kind of go here, 1, 2, 3, 4, 5, 6, 7. 10 to the 7. So the answer is C. So let's go one step a little further here. We're going to use scientific notation with something astronomical. So our Milky Way galaxy, a lot of astronomers think that our Milky Way has 100 billion stars in it, at least. And if there's 100,000 stars in our local supercluster, how many stars do we have in our local supercluster? A, B, C, or D, or E? Anyone? C. So the answer is C. So 100 billion, you add up the number of zeros after the one, just basically the number of zeros you have when you add them all up. We have a number that has 16 zeros. Okay, let's try something a little different. Okay, he kind of developed this graph here, and what it shows is it's a plot showing temperature going from high temperature to low temperature, and brightness over here on this scale from low to high. And he plotted a bunch of different stars, and here's where Betelgeuse plots. So his question is, which star on the graph below has a temperature most like that of Betelgeuse? So just reading that graph.
D.
I heard, did I hear D?
D is in dog.
Delta.
No, B is the right answer. Because here's the temperature. This is the temperature axis. So, and Betelgeuse is directly over top of that. B is actually going to be a little cooler than Betelgeuse, whereas temperature D, even though it's a lot less bright, it has the same temperature as Betelgeuse. So it comes to like just being able to look at graphs and be able to kind of sort that out. That's basically what he was doing. Does that kind of make sense? I don't know if that's... I got that one wrong, actually, when I did it. I was fooled by B being really close there. So here's one that's a little different too. This is a graph that plots the distance of a galaxy in millions of light years with the speed at which it's receding from us. So the farther away a galaxy is from us, it's receding from us faster. So that's sort of the plot that was made of these galaxies here. So the question is, if a galaxy were discovered to be 2,200 million light years away from us, what would be a good estimate of its speed? So that would kind of plot it here. That's 2,200 million light years. So what do you think its speed would be? Which one of these is sort of the best answer?
25,000.
25.
E.
Correct. Yep. So that's just extrapolating to plot it. Okay. Here's one here. This is just using angular measurement. Measuring angles has really done a lot in astronomy. Most of the objects are just too far away to measure them directly, so they try to figure out its angular size to try and convert that to an actual size. So this is an earthly example here. So if we're out and we see a boat on the horizon and we measure its angle, and it happens to be 5 degrees from there. So we go from there to there, and that's an angle of 5 degrees. How many boats could you put all around you if you lined up the boats that size and put them all around you in a circle? How many boats would there be?
C.
C. Here,
Yeah.
C.
C.
C? Correct. C. 360 divided by 5 is 72. There's 360 degrees in a circle. Okay. And the author of this, he noticed that almost none of the textbooks in astronomy talked about probability. He said they'll go on and on about extraterrestrial life and extraterrestrial intelligence, but there's nothing about probability. And so here's this. If you flipped a coin 6 times and it came up heads each time, what would be likely to happen on the 7th flip?
C.
50.
Well, it depends if you're betting on it.
Yeah, of course. Equal chances every time.
Trevor,
Doesn't have
the
any-
second line, is the word astrology
But this is
supposed to
astrology
be there?
during- yeah.
Yeah,
There to compare.
the textbooks will even discuss astrology. Yeah.
Okay.
And the search for those
Yeah.
2 items
Which is, that may not be the case now. This report, or this paper was published in 1990, so the textbooks may have changed since there.
What they should have about astrology in textbooks is never ask an astronomer your sign.
Oh, yeah. I know.
But we all know our sign.
'Cause I'm an Aquarius and I'm really skeptical. Okay, that's enough of the math. So here's a question about the solar system. Objects that can be seen with the unaided eye and appear to move against the background stars during 1 month. So you're out looking over a period of 1 month and you notice that there's some objects in the sky that are moving against the background stars. So what can you tell about them? Which one is most likely to be true? I think I heard B.
Yeah.
Yeah, they're within the solar system. They're probably
The travelers.
planets or comets or something within the solar system. Now here's one that gets you to kind of think about a frame of reference. So here's this nice little diagram here. If this is the sun, and you're a person in orbit above the north pole of Jupiter, and you're looking back toward Jupiter's moon Europa, how would it look to you from being in that location? Yeah. Good. This one I thought was kind of interesting. Did you see that already? Yeah, that's on there. I might move this a little bit. Okay. The numbering might be a little mixed up. So which answer shows a pattern of closest object to the Earth to the farthest object from the Earth? I think I hear that right.
C.
C. Yep, C. The moon and the sun and Saturn. Okay, we're going a little further out. Same thing. The ISS is the International Space Station. For which order? E. Yeah. E. International Space Station will be closest, then Pluto, and then beyond, well beyond that, the stars. So E for that one. Okay. So the Big Dipper. Most of us, or all of us, have probably seen the Big Dipper. Let's say you went someplace else. And where would you have to go for the Big Dipper to have a noticeably different shape to the unaided eye? Very good. Everybody hear that?
Yeah.
A. Okay, now we're going out even further. This one's on galaxies. Which answer shows the pattern from closest to farthest from the Earth?
E.
I think I heard it out there. Everyone agree that it's E?
Yeah.
Yeah. Andromeda Galaxy is farther away than the Milky Way. The center of the Milky Way. Okay, this is a little different. The best place to look for galaxies. So if you're going out on a night with a telescope and you want to see galaxies,
D.
what would be a good place to go? So these are not the Milky Way, but galaxies that are outside the Milky Way. Galaxies different than the Milky Way.
C.
Here's C. No.
No.
C wouldn't be very good because the Milky Way would be in the way. You wouldn't be able to see galaxies.
Depends on what kind of galaxies you're looking for. I would mention
Now this question I have a problem with because it uses the word best. It should be a place to see a lot of galaxies is
D.
anywhere away from the Milky Way.
Of course, if you misinterpret that and think, where should you be, then you should be near the moon.
Yes. If the moon is in Virgo, then near the moon. But of course, if the moon's there, you won't see as much. It's smaller.
No, but if you're on
orbiting
back.
Oh, you're on the moon.
That's what I mean.
Okay, this is a thought that kind of tries to probe students' understanding as to what's happening to the size of the universe. So when the observable universe was half of its present age, it was which of those? B. It was smaller. So when the universe was a lot younger, half its present age, it was a lot smaller than it is now, which means that the universe has been getting larger. and continues to get larger. Okay, then we had a bunch of questions on light and color, how light and color behave. These were getting a little more into physics. So hopefully everybody can read that okay. So you're in a completely dark room. There's no light and there's no windows. Which group of objects do you think you might be able to see?
None of them, no. It is completely dark.
It's completely dark.
None. I've been in the dark room.
So, and this was kind of a tricky one because you think that, oh, I could probably see a bicycle reflector. I see those at night, but you see them because there's light. But if there's absolutely no light, then you won't see any of them. So this one's similar. Here's one. I'm standing at the end of the rainbow here. Okay. So it's nighttime, and headlights from a parked automobile light up the road brightly from point A to point B. So if this fellow is standing way over here at point D, he can see the headlights glowing. So which statement is sort of which statement best describes the farthest point that the light from the headlights can reach? So how far can the light reach from those headlights?
It's not very bright. It's E.
I think I heard the right. E. So the answer is E, and that just means that even stars that are very, very, very far away and you can't see them with the naked eye, the light's still getting to us. You might just need a much larger telescope in order to capture enough of that light to make it visible. Okay, this is the same car, but it's in the daytime. So it's in the daytime. He has his lights on. The person standing in the same spot can see the headlights glowing. This is the sun shining here. So this is just the same question, only it's in the daylight. So car is parked where it is. It has its lights on. Person standing at D can see the headlights. You can see they're on. So which one is true?
Still E.
It's still E. Yeah. So just because it's almost getting to the point like in the daytime when the sun is out, there's still stars shining up there, but the light is still there. It's just that our eyes can't see it. But if the person standing here can see the light from that, then we know that the light's getting that far. And this is another one like the Jupiter one. This has to do with the way shadows go. So this one's a little long to explain. So here we are. We have two lights. One light is on and the other one is off. And when light A is on, it casts a shadow like this. Like that. So this question is, what would the shadow look like if both of the lights were turned on? So which one of these would be E? Yeah, I think everyone got that one, right? Yeah. It's really surprising. Like apparently a lot of the test people that took the test had a lot of trouble with some of these questions.
Because, if you see any old TV series, and then you see immediately if something is done in the studio instead of outside, because you have double shadows or whatever.
Yeah, yeah. Well, yep. So yeah, D, there'd be two shadows. Okay, this one's a little more involved. So here we have two stars, A and B. They look equally as bright in the sky. However, we know that star A gives off a lot more light than star B. So if that's true, which of the following is true about star A? Okay, so star A and B appear equally as bright, but star A gives off a lot more light than star B. If that's the case, which is true about star A?
Any of this is right.
Star A.
Oh, star A is.
Star A looks the same brightness as B, but we know that star A actually gives off a lot more light.
Okay.
If-
Then
if-
Star A gives off a lot more light, but
farther
it looks
away
the same
from-
brightness
yeah,
as star
maybe
B.
B.
This is really getting into it. So, like, which one do you think?
B.
B.
Everyone agree B?
Yeah.
Yeah, B. And actually, the stars I took, this is my star in the Big Dipper, and that's Polaris. So my star and Polaris almost look the same brightness in the sky, but Polaris is much, much farther away, but it's a lot
On
brighter.
that one, it's possible to be E, not likely, because it can give off more of the same diameter. It would have to be at about the same distance.
And-
Like there are conditions in which another answer is possible.
And there is another problem, there is extinction. If you come closer to the horizon. So you have another factor.
And then branding on the Milky Way.
There's always problems, right? There's always something.
And then there's clouds.
Yeah, those clouds, they just.
Yeah.
I know. That was one of the clearest nights on that trip. Okay, here's another one. This has to do with how we know how light propagates. This guy's reading a newspaper by the light of a candle 1 meter away from him. So if the candle holder was moved 2 meters away, how many candles would he need to be able to read the newspaper with the same amount of light? I think I heard D a lot.
D, yeah.
Okay, so you guys know that light propagates to the square of the distance. This is the same question, just kind of worded differently. Saturn is 10 times farther away from the sun than is the Earth. So from Saturn, the sun would appear, which one of these? It's like some people are still thinking.
E.
Yeah, E. Saturn's 10 times farther away, so it's 100 times dimmer, or 10 squared dimmer. So that makes me think about, Titan. Jerry gave a little chat about Titan today. That the pictures that we're seeing from Titan are of a place that has only 1% of the light that the Earth receives. So I read somewhere that under the clouds of Titan, even at noon, if the sun's right overhead, it's like a cloudy day about 20 minutes after sunset, like really dark and gloomy. And I think that's the last one. I had a bonus question here. I think we're almost ready to go. I left this one to the last because this one I didn't get either. I had to do math. It's like, it took me a while to figure out what I had to do to calculate this one. So let's see how you guys fare. So here we have, somebody's looking through a window. And what we know is that this window is 1 meter from top to bottom. And we also know that the house that's across the street is 8 meters tall. So the question is, how far away is the house? Well, this is kind of getting to how astronomers figure out the distances to things. They often can't measure it directly, so they have to do mathematics to kind of come up with these answers.
You gotta use cosines.
Yeah.
Yeah,
That's not fair.
So you don't need trigonometry for this, I discovered. But you do have to know a little bit of geometry. So what I did is I redrew it because it was just kind of confusing for me to be standing there and looking it that way. To me, it was easier for me to figure out if I were like down the street and looking at it in plan view. So I did it this way. So here's the window, 1 meter tall. I'm standing here. I'm 2 meters away from the window. and here's the house. I don't know this distance here, and that's 8 meters. So at first I thought it was congruent triangles, but they're not congruent triangles. They're similar triangles. So if this is 1 meter and that's 2 meters, this is 8 meters, and this has to be 8 times as much as 2 meters, so 16 meters. So I didn't get this one. So some of you here, if you got it, then great, you're awesome.
So
You
the
know
house
math.
is 16 meters from the window or from the observer?
From the observer. Yeah. And I think I got thrown to it because a lot of the answers before that were like these, and like they were like over here, and then I kind of got, well, why is it that one? I got sucked into the trap of doing a multiple choice test. You know, there's no patterns to the answers. So anyway, that was that one. So, and that was the last one.
Good, thank you.
So,
Oh,
there you go.
very nice.